there are a lot of things I wish to talk about. First is properties of sound waves, different comparison that we have to do between solids, liquids and gases, because whenever I am talking, there is a continuous reflection from the walls. Refraction of sound, audible sounds have wavelength of about 1.5 centimeter and diffracts by small size gap, so you do understand. So refraction of sound waves, so it is again nothing new for you. It is basically the change in direction of sound whenever it travels from application of ultrasound. So sonar, sound navigation and ranging is a method used to measure the depth of water. Hello students, welcome all of you. Today we are continuing with our series on waves. So many things we have already talked about, students. If you remember, we have discussed what waves exactly are, what are the various properties of wave, then we talked about the water waves, then we also talked about sound waves in our last class. But as I had told you, the main two waves that we mostly come across is sound and of course light. So today we are discussing light, right students? So without wasting any time, I will give you the time, put down the heading, light waves or simply light. Right students? So when we talk of light, you have in a way an understanding of it. Light is a form of energy, we always say, but basically what happens is it is basically the propagation of energy, right? So light is the propagation of energy. Now how does this energy propagate is very different from what we have discussed so far, where we were discussing while wave is propagating, it is the medium particles aid or assistance that let it happen, right? So it is the next particle and next particle. Here it is completely different. Light waves are electromagnetic in origin. So they travel with the help of electric and magnetic fields, which we will study in the next unit. So the prominent thing here is, or the highlighting thing here is, that light does not need medium to propagate. So that is the first thing that you should keep in mind, that while this energy is propagating, it does not need medium. In fact, vacuum or free space, it can easily travel without any hindrance, right? All right, so one by one, let's talk about things here. So light, you understand, it is transverse wave. If we talk about the behavior of light wave, it is transverse. That means the electric and magnetic fields, so called, which you might not be knowing, but don't worry, they are always perpendicular to the direction of movement of wave. That is what transverse wave are, right? So light reflection, you can see an object only if light from it enters your eyes. So of course we are only able to see things because of light, right? So imagine there is dark in the room and there's no source of light, then you won't be able to see things. But when you switch on the light, what happens is light gets reflected by those objects. So it is the reflection of light by the objects that gives us this facility of viewing things, right? So you can only see objects if light enters your eyes. Some objects such as sun, electric lamps and candles make their own light. They are luminous, right? We call these objects luminous sources. Most things are non-luminous. They do not make their own light but reflect light from a luminous source. So all this is just to give you a feel of things. Then light waves are transverse electromagnetic wave that travel in vacuum with the speed 3 into 10 raised to the power 8, and we have discussed this, that light speed is way more than speed of sound. That is why you always see things first and then you listen to the sound of it. So for example, lightning is the best example here. You see the lightning first, but the sound reaches you with a delay. That is because light travels at a way faster speed, but this speed is in vacuum. Other medium will have different speed of light. As you know, that wave speed depends on the medium, right students? Then speed of light, or any wave for that matter, you do understand, is product of f and lambda. Light travels in straight line, so it can produce shadows and inverted images. This is one thing that we almost assume, that light keeps propagating in a straight line. That is called the rectilinear propagation of light. So that is called a light ray. So normally you associate light with rays. So when you say ray, a ray has a starting point, So, let us say it is a luminous object, then this is the starting point, and then we can say that light is propagating. So, it is somewhat like this, right, and then you can draw an arrow. So, it has a starting point, but it does not have an end point. So, it will keep propagating further and further and further till infinity in whatsoever. If there is no hindrance, if there is no reflection, if there is no abruptness, it will keep propagating. That is why we talk about light years and stuff like that. Light keeps traveling for years and years and years without any problem in free space, right? A bundle of light rays is called a beam of light. So, if now you have a collection of light rays for that matter, then it can be somewhat like this, then this, then this. So, this can be treated as a bundle of light rays, which we may call it as a beam of light, right students? This is called the beam of light, not necessarily a parallel beam. It can be a converging beam, okay, like this, or it can be a diverging beam. But students, keep in mind, this arrow is very important. This tells you how the light is going. So, for example, in this diagram, it's going from left to right. If I draw the arrows like this, then you would know that the object is on the other side and light is coming in the other direction, right? All this you can write, then we move forward. Right, students? So, the next thing, very quickly, laws of reflection. So, you do understand, we have talked about it. The angle of incidence is equals to the angle of reflection. This is the normal. This point is referred as the point of incidence. What do we call this? Point of incidence. While this is the incident ray, this is the reflected ray. What causes reflection, students, is normally a shiny surface. So, you would see a good reflection only in shiny surface like silver, right? You won't expect this reflection to be that clear in other objects. So, it can be an abrupt surface like this. Then what happens is that light gets reflected in different directions, and this is not a regular form of reflection. Then this is called diffused reflection. This is called, just for your knowledge, so if you want a good amount of intensity of light after reflection, you need a flat, a finished, a shiny surface like a mirror. So, that is what mirror is, a silver surface which is covered with glass. That's mirror for you. These are the wavefronts, as you know from our previous classes. So, reminding you, you will only be able to understand things what I am discussing today if you have already watched the previous videos of this series, right students? So, this is the incident ray, this is the reflected ray, this is the normal at the point of incidence, then this is referred as angle of incidence, this is referred as angle of reflection, right? So, this is one thing, and the other is that incident ray, reflected ray and normal all lie in the same plane. So, now listen to this. For example, if I tell you that angle of incidence is 60 degree, then the angle of reflection also needs to be 60 degree. But which ray? So, if for example, this is the incident ray and this is the normal, you can have infinite many rays at 60 degree. So, how would you know which is the reflected ray? So, it is the one which is lying in the same plane. So, if light is coming from here, then the reflected ray has to go like this. If light is coming from here, then the reflected ray has to go like this. So, it has to lie in the same plane, all three, incident ray, reflected ray and normal all lie in the same plane. This is another law of reflection, but today what we are focusing on is this law, that the angle of incidence is equal to the angle of reflection. Write everything, then we move forward. Alright students, next thing is how to draw a ray diagram to find the position of image made by a plane mirror. So, you do understand that is the most common reflection that you can relate with when you view yourself, when you view your image in a plane mirror, right students? So, understand that the image is obtained by at least two rays. Now, what is that going to mean? So, for that I will tell you one thing here, that is a secret, and that secret is that you always go with the normal ray. You go with the normal ray. So, you think about, what if a ray is incident along the normal, that is the angle of incidence is 0 degree, then the reflected ray will go back in the same direction. Imagine if I is 0, then R will also be 0. So imagine if I have a ray, let's say like this, then it will go back like this. In a way, we can say that it will retrace its path. That is when I is 0, R is also 0. So you can think of it like that. So if, let's say this is the incident ray, okay, let's say this is the incident ray which is along the normal, okay. So what is going to happen is it will get reflected back. So while reflection is happening, I'm again reminding you, the frequency does not change, the speed does not change, the wavelength does not change. So it will go and come back along the same path. I is 0, so R is also 0. Now think about another ray. Which let's say is incident at this point. What is going to happen? So I will draw the normal here, right, students? This is, let's say, theta 1, the angle of incidence. So what I should do is try to make a ray which is almost similar angle. So let's say this is theta 1 again. So this is the incident ray and the reflected ray. So let's call it I1, then this is R1, incident ray and the corresponding reflected ray. Now think of another ray, let's say incident here, okay, students. So we need at least 2 rays, that is the idea, okay. So let's say this is theta 2, then the reflected ray will again be same angle approximately, let's say theta 2 again, right. So these are the rays that are being reflected. So how do you see them? They are all diverging, they won't converge, they won't meet at a point, So what I am going to do is extend them backwards, because we do visualize light to travel in a straight line. So when we are the observer here, let's say you are here, okay, so this is your eye. So what you are going to see is somewhat like this, okay. In a way, this is going to be your image, right? It's not exactly to the scale, but this object you will see as if the rays are coming from here. That is how you see your image. What are the characteristics? So this distance, let's say if D, then this distance is also D. Imagine yourself, you're in front of the mirror. Whatever distance you are at from the mirror, your image is at the same distance behind the mirror. So this is one point. Image distance is same from the mirror as the object distance. So if you are 2 meters away, your image will be 2 meters away as well. What is the next thing? It is erect. So if you are standing like this, let's say, your image will also be having your head up and toes down, right? No doubt about it. But there is a problem. Your right hand in the image will become your left hand, right? So if I write P for physics and hold it in front of a mirror, then it won't look like a P like this, but its mirror image will be like this. So in a way, it is a lateral inversion. So the image is laterally inverted, the right side becomes the left side becomes the right side, right, students? This is called virtual image. We call this as virtual image because it is not formed by actual meeting of rays. You see the rays are coming from that point, but the rays were never there. So this is a concept of virtual image. When rays are actually there, you call it as a real image. Don't worry, I will discuss that. I'm just wanting to discuss how to draw the image. So I have used these 2 rays. If you can just take the leverage and use this ray as well, all 3 will appear as if they are starting from somewhere here. So this O will have its image here, right, students? I hope you are able to understand how a plane mirror is used. And don't worry, all these things we will do a lot of times when we will be solving previous year papers, and there you can get your skill polish over there. All right. So the next thing now, students, is characteristics of plane mirror image. It is virtual, it is erect, it is same size of the object, it is behind the mirror, and it is inverted, but it is laterally inverted. So when I say inverted, it is laterally inverted. Like vertically it is erect, so you are still having your head and toe in the right position, but your right left has demolished completely. Right has become left, left has become right. So, real image is formed by actual intersection of real rays, can be captured on a screen. The best example I could have thought of is the projector. So, when you use a projector, you actually throw the light through the lens on a screen, and that is what a real image is like. While this is of course not on a screen, this is not actual rays. Imagine you are seeing yourself in the mirror. Wherever you are seeing yourself, you cannot have your image on the screen over there. So, it is because the rays are actually not there. If you look at the previous diagram, wherever you are seeing yourself, the rays were never there. So, if you have a screen placed here, you will never be able to see yourself on the screen. Alright, I will wait for this. You can write down the important stuff, then we move forward as usual. Alright students, next thing very quickly then, refraction of light. We have discussed this today, we will discuss it even in more detail. So, meaning of refraction, so you do understand that it is the bending of light whenever there is a change in the medium. Examples of refraction in glass: refractive index, critical angle and total internal reflection. So, this is something that we will discuss in the next class. So, this we are not doing today. I don't think the time would permit that, and that would be way too much of information. So, we are starting off with the three things that you are seeing. So, the bending of light when it passes from one medium to another is called refraction of light. A pencil placed in water appears to be broken due to refraction. Of course, you have seen that. You put something, you put a rod or a pencil or a pen inside water, you will see as if it is broken, because the rays that appear from here will be bent. Once they are bent, they don't appear to be at the same spot as they are, but since you have the remaining pencil still outside water, you see them in a different direction. So, that is why the pencil seems to be broken at the point of surface of water, right. During refraction, speed and wavelength of light changes. This is nothing new, we have discussed this. While refraction happens, the speed changes, the wavelength changes students, but the frequency never changes, right. Copy down the important stuff and we will talk about things in detail now. Alright students, so now the math part starts. This is where a little math is involved. That is when we talk about laws of refraction students. So, it's the ratio of, so first we are defining another term, that is refractive index. You can also call it as the optical density. So, it tells you how dense the medium is, how difficult it is for light to move. So, we are discussing only transparent medium here students, not opaque things. So, transparent medium you can think of like air, like glass, like water, like diamond. Light doesn't travel with the same speed. So, we define refractive index as, let's say we denote it by n or mu, whatever symbol you may use. Sometimes we use n, sometimes we use mu, you can use any of the symbols. So, let's say we are talking about n. So, it is inversely proportional to the speed of light in medium. What is it? Let's understand. More speed is less optical density. So, imagine let's say diamond and vacuum. Vacuum light travels fastest, diamond it is slower. So, diamond will be treated as denser medium as compared to vacuum. Okay. So, we define refractive index as the speed of light in air, which we definitely mean by air, we mean vacuum here, because vacuum and air are like almost the same, there is hardly any difference. So, speed of light in vacuum divided by the speed of light in medium. So, for example, if we have more speed of light in the medium, then the refractive index is less. If this is less speed of light, then refractive index is more. So, if we say that the refractive index of diamond is more than that of water, we mean that in diamond light is travelling slower, in water it is travelling faster. So, more refractive index means more dense the medium and lesser the speed of light in that medium. Students, please note down this, that refractive index is defined as speed of light in air to the speed of light in medium. I have given you an example for glass. So, glass you can see that the speed of light in glass is 2 into 10 raised to the power 8, while in air it is approximately 3 into 10 power 8. So that gives you the refractive index of diamond as 1.5. For diamond it will be even more, like 2.42. So light speed is even less, right? Now what is this Snell's law, student? This is very important that we are discussing next, that what are the laws of refraction, though I have it on my next slide, that what is Snell's law, but before that, we will discuss it here. So what are the laws of refraction? So this is the main law, which is called the Snell's law. So what is Snell's law, students? So it states that, sine, that is sine, S-I-N-E, sine of angle of sine theta cos theta, sine of angle of incidence to the sine of angle of refraction is a constant that is equal to the ratio of refractive index of second medium to the refractive index of the first medium. First medium we always treat where the light started from, and second medium where the light is going after refraction. So can I write it like this? N1 sin I equals to N2 sin R. Students, that is how I want all of you to remember this. N1 sin I is equals to N2 sin R. So the refractive index of this medium multiplied by the sine of angle is equals to refractive index of the second medium and multiplied by the sine of angle of refraction. That explains one thing, that if N2 is greater than N1, which is the case here because air to glass, right? So light is going from rarer to denser, rarer to denser. You can consider this as point A, right? So if light is going, so if N2 is more, if this term is more, students, pay attention. If this is more than this, then this has to be less than this because the product is the same. You can do this much math. So this implies R is going to be less than I. So we have used this so far but never derived it. Now you can understand R is less than I means light will bend towards the normal. Light will bend towards the normal. Every time we have discussed this, that whenever light goes from rarer medium to denser medium, rarer, denser, light will bend towards the normal, and vice versa. When it is going, imagine from here to here, let's say this is the second point and again the transition is about to happen, air, glass, again air. What is going to happen now? It will bend away from normal again. Why, students? So let's call it I2, then this is R2. So again, now what happened is just vice versa of this. Let's call it as point B. Students, what is going to happen? Can you imagine? Now it is going from denser to rarer. So speed of light has suddenly increased, denser to rarer. So now it's vice versa. Now R2 will be more than I2. Why? Again, following the same logic, R will be greater than I because now the second side medium is rarer and the first side is denser. So keep this in mind. Two things I will revise again because it is too much of information in this one. First is how to define refractive index of a medium. It is the ratio of speed of light in air to the speed of light in medium. More the speed of light in medium, lesser the refractive index, lesser the speed of light in medium, more the refractive index. So if I say diamond has more refractive index, that means it has lesser speed of light and vice versa. Then sin I over sin R is a constant that is always equal to the ratio of refractive index of the second side to the first side, but I rewrote this as this, N1 sin I equals to N2 sin R because that is how I will use this, right? Copy down the important stuff, then we move forward. Alright students, so I think you must have paused the video and copied down the important stuff. Now you can understand why in fact this light ray is going to be parallel to the initial direction of motion. Why? Because when you wrote this, so this is like I and R and I dash and R dash. So let's say the refractive index of glass is N. One thing students, what about the refractive index of air itself? So when you say the refractive index of air, so that in that case this will also be air and this will also be air, so this ratio will become 1. So that is the minimum refractive index you can have, vacuum or air, you treat that as 1. Any other medium you will have more refractive index because of the lesser speed of light, right students? So let's go back here. So when let's call it A and let's call it B, So at A, what you're going to write is 1 into sine I is equals to n into sine R, isn't it, students? Where n is the refractive index. Now this is a glass slab. When we say a glass slab, it is like parallel faces. So these normals are also parallel. So whatever is R here is equal to the I dash here. Can you visualize that, students? And if that is the case, what you can write on the next face B, n into sine I dash equals to 1 into sine R dash. But since I dash is equals to R, you do understand that this can also be written as n into sine R is equals to 1 into sine R dash. And if you can clearly see now from first equation and second equation, like n into sine R, n into sine R, this is sine I, this is sine R dash, this implies R dash is equals to I. So this light is going to emerge parallel to the initial direction of motion. This is very important, students. Even if you don't understand the whole math of it, what is important for you to understand is that this is the incident ray, then the refracted ray, the emergent ray eventually will be parallel to its initial direction of motion, slightly shifted. You can call this as lateral shift, okay, but it has to be parallel, okay. So you can watch this again and you will understand the steps, and when you will write this you will have a better understanding. Sure, but now this is like a triangular slab, like a prism. So when it is a triangular slab, these two faces are not parallel. Of course they are not, right? So what happens is light bends, and let's say this is R1, this is R2. It first bends towards the normal, then it bends away from the normal, and eventually it is going like this. While it was supposed to go on this path, now it is going on this path. So we call this light has been deviated. It has suffered a deviation. It has suffered a change. That is what prisms do. We will talk about them in detail in the upcoming classes. You can copy down the important stuff and then we move forward. Right, students? So the next thing that we have to discuss, from rare to dense, we do understand that speed of light decreases, wavelength decreases, but one thing that never changes while refraction happens is the frequency, right? And what happens when light is going from rare to dense? It bends towards the normal. When it is going from denser to rarer, it bends away from the normal, right? Angle of incidence, all this you can think about yourself. You don't need my assistance in this. I think we can move forward now. Now let's talk about the apparent depth. So what is the apparent depth like? So whenever you are seeing a swimming pool and you are visualizing the floor of the swimming pool from outside, it is deeper than you think. Like it is virtually lifted. Why does that happen? Let's say there is a coin or something like that at the bottom of the water body. Can you imagine this? Let's say a ray of light that goes straight. This is my favorite ray. Why? Because if I is 0, can you imagine this now, students? If I is 0, angle of incidence is 0, angle of refraction is also 0, and the ray does not bend at all, right? The ray does not bend at all and it will straight away pass. Okay, so for this ray I is 0, then R is also 0. Now think about another ray, let's say, which is incident here. Okay, so now this is going to be the normal, and this is, let's say, I. Then the ray is going to bend away from the normal, right? Why? Because it is going from water into air. So it is like going from denser to the rarer medium, student. What does that do then? It will bend the ray away from the normal, right? It will bend the ray away from the normal. So when you visualize these two rays, these will never meet, and virtually it will feel as if the rays are coming from this point. So this will have a virtual image over here. So when you are visualizing things from outside, you won't be able to realize that this object is here, but you will virtually feel as if it is lifted. That is the apparent shift. So it shifts its position from here to here virtually. What is the reason behind that? The same reason why the pencil was looking broken. That is the reason, that is the refraction. So anything that you are seeing from outside is not the actual position of the objects. they are slightly shifted or uplifted from their actual position when you are visualizing them from outside. So now I hope whenever you see a coin in any swimming pool, you're playing some game to find the coin, you should be able to realize that refraction has a role there and the coin is not exactly where, but once you go inside water, then there's no refraction. But if you're visualizing it from outside, that's not the actual location. Right, students. So let's do one last question before ending today's class. Then we will talk about the various aspects of light waves in the upcoming. It's a big unit, this waves, but then there is a lot to learn also. You can take it as an opportunity. I take it as an opportunity. So figure shows a ray of light passing through a rectangular glass block of refractive index 1.5. If the ray strikes the surface PQ at an angle of incidence 60, as you may see, calculate the angle of refraction at the boundary PQ. Right, students? So we will write 1 into sine I equals to n into sine r. Now what is I, students? It's 60 degree. What is n? It is 1.5 for glass. Now what is sine r? Something that we don't know. So the value of sine 60, so we can use the calculator here. So sine 60 divided by 1.5, I'm getting 0.577. Let's do sine inverse of our answer, and I am getting r as 35.26. So let's take it as 35 degrees. Right, so that is the angle of refraction. It has bent towards the normal, isn't it, students? 60, and this has become 35. Now this 35 will also make this as 35, and this will again be 60, students. Even if you apply Snell's law at the second phase RS, you will get the answer as 60 only. You can verify it for yourself. So angle of refraction, so the answer is 35 degree. Then angle of incidence X in the glass block, that will be again 35 degree. Why, students? Because these two are parallel, so their normals will also be parallel. So if these are like alternate angles which are going to be equal, of course you know that. Now this is again going to be 60 degree. Easy, students. I hope you were able to understand whatever discussion we've had about light. So light is a part of electromagnetic waves. There are many more waves. We will discuss in detail about those waves like radio wave, microwave, ultraviolet waves, infrared waves and whatnot, but light is a part of it. And I hope you are able to understand now that how light is a wave. It is not a particle. Light is spread everywhere whenever you turn on or switch on any light source in your room, right? So that is basically electromagnetic wave. Right, students? Thank you so much for your time. I hope you are liking the work we are doing to elevate your result. And if you're really liking it, please let us know by liking, sharing and subscribing to our channel. Thank you so much for your time. I will see you soon with the following up videos and the remaining part of this particular unit. Right, students? Thank you. Bye-bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.